Okay, this is from the ACS Organic Chemistry Official Guide, second edition. And 3, structure, constitutional, stereochemical, and conformational isomers. All right, and I'm going to be solving the practice questions in this video. So let's start with the first one. How many stereocenters are present in this molecule? And so you can see we kind of have 3 contenders here, maybe here, here, and here. Well, you can see the one that I have highlighted in yellow is not a stereocenter. Okay, this is not a stereocenter, and it's because this carbon is attached to 2 methyl groups. So even though they used a dash there, that is not a stereocenter. All right, so I'm just going to erase those methyl groups. So we figured out the first one is not a stereocenter. So that means we've got to have either 2 stereocenters or 1 stereocenter, trying to solve this a little bit by the process of elimination. The one that I have highlighted in red is certainly a stereocenter because this carbon is attached to this isopropyl group, the bromine, the hydrogen, which is not shown, and then this group over here. So that is definitely a stereocenter. And then the carbon that I have highlighted in green is also a stereocenter, right? There's a hydrogen that is not shown. There's a methyl group, there's a cyclohexyl group, and there's a group over here with the bromine on it. And so the answer is 2 stereocenters in this molecule. All right, let's take a look at number 2. Which of the numbered carbons in this compound are stereocenters? Well, you can see we have carbons 1, 2, and 3 numbered here in this structure. Number 1 certainly isn't a stereocenter, is it? Because it's got 2 hydrogens attached to it. Those 2 groups are identical. And so we can get rid of answer A and B. So now we need to figure out whether carbon 3 is a stereocenter or not. It certainly isn't because it's sp2 hybridized. Okay, so that's not a stereocenter. And so the answer is C. Only carbon number 2 is a stereocenter, and you can see it's attached to a hydrogen atom. It's attached to this sp2 hybridized carbon. Then it's attached to 2 sp3 hybridized carbons, but one goes to this carbon off of the bridgehead here, and this other one goes to a methylene. And so those are 2 non-identical carbons. And so only carbon 2 is a stereocenter. All right, let's practice a little bit of the Kahn-Ingold Prelog rules, which is assigning R and S, R or S, I should say, to a stereocenter. And so what are the absolute configurations of these 2 molecules? Well, if we look at the first one, okay, number 1, we can see that the sulfur is going to take the highest priority on our chiral carbon because sulfur has a higher atomic number than any other atom in here. Then we have the carbon that is attached to oxygen, this carboxylic acid. So that carbon is attached to 3 oxygens. Remember, a double bond to an oxygen is considered like 2 single bonds. So this is going to be group number 2. Then we have a methyl group and an ethyl group. Well, when you're looking at straight chain groups, the more carbons you have, the higher priority it takes. And so this is going to be group number 3. And so our lowest priority group is coming out towards us. So what we're going to do is we're going to go from 1 to 2 to 3. And so this is going clockwise, which would be R, but since our lowest priority group is coming out towards us instead of being in the back, we're going to flip that and change it. And we're going to say this has an S stereocenter. All right, and if we look at the Fisher projection in number 2, we have the hydrogen, which is going to be the lowest priority group. We have the oxygen, which is highest priority. Now this carbon on the top is attached to a bromine, so that's going to be second highest. And then we have the ethyl group, which will be third highest around our stereocenter. And so we go from 1 to 2 to 3. And so this is going counterclockwise, which normally would be S. But remember, since this hydrogen is horizontal, it's on a wedge. And so we must flip that. And so that would be an R stereocenter. And so the stereochemistry for compound 1 is S, and the stereochemistry for compound 2 is R. And so the answer is going to be B. So remember, when you're assigning a chiral center as R or S, that's called the Kahn-Ingold Prelog rules, or we employ the Kahn-Ingold Prelog rules to designate a stereocenter as R or S. All right, next question. Which molecule has an R configuration? And if you look at the first compound, we'll just go through these quickly. The hydrogen's in the back. We have the highest priority group, the alcohol. The oxygen has the highest atomic number. or a higher atomic number than these two carbons in the hydrogen, obviously. So we're going to go from 1 to 2 to 3. And so that's going counterclockwise. And so this is an S stereocenter. In B, we're going from 1 to 2 to 3. The hydrogen's in the back, going counterclockwise. And so this is an S stereocenter. In C, we're going from 1 to 2 to 3. And so that's going clockwise. And so that must be our answer. Now notice in here that the lowest priority group is the methyl group that's in the back. And then in the last one, D, we go from 1, where alcohol is, over to 2, where nitrile is, 3, the methyl group, hydrogen's in the back. And so this is an S compound. So the answer is going to be C. Now, question number 5, I would say that this question would probably involve the use of some scratch paper, but I'm just going to try to solve it here quickly in this video. What is the molecular formula for an unsubstituted alkane of smallest molar mass which possesses a stereogenic center? So remember, stereogenic center is just the same thing as a chiral center is all it means, or asymmetric center. They all mean the same thing. So stereocenter, chiral center, whatever, stereogenic center, they all mean the same thing. Well, if you think about C5H12, well, there's only a couple of isomers possible, right? So if we have 2-methyl butane, that doesn't have a chiral center in it. And then if we were to have 2,3-dimethyl propane, which is or sorry, that's neopentane, I think, that doesn't have a chiral center in it either. So there's no chiral centers there. If we go to B, all right, so maybe I'll use my black pen for B. So we have 1, 2, 3, 4, 5. And then if we add a carbon here, if we have 2-methyl pentane, that doesn't have a chiral center. And if we put the methyl group here to make 3-methyl pentane, that doesn't have a chiral center either. It's not until you get to 7 carbons. So if we do 1, 2, 3, 4, 5, 6, sorry, 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6. And then if we were to put a methyl group here, this carbon, let me highlight it in yellow. This carbon is a chiral center because it has an ethyl group attached to it, a methyl group attached to it, and a propyl group attached to it. And so it has a chiral center. So the stereogenic center is going to be this carbon right here. And so the answer is going to be C in this case. All right, number 6, which Newman projection best depicts a gauche interaction between two bromine atoms? So remember, a gauche interaction is when we look at our Newman projection and we have a dihedral angle of 60 degrees between two substituents. And so you can see that here we have the two bromines that are gauche to each other, right? Remember, this dihedral angle here is 60 degrees. Maybe I should just say here this is 60 degrees. Okay, so that would be a gauche interaction. Note that in B, the two bromines, if you remember, when they're opposite of each other like this is called anti. So these are anti to each other. So anti and gauche. Anyhow, another thing I would just comment on here is if you look at the first 3, okay, the first 3 Newman projections, they're all staggered, whereas D is eclipsed. So the answer certainly isn't D. All right, number 7. Which Newman projection represents the most stable conformation of 3-methylpentane when viewed down the carbon-2,3 carbon-carbon bond? So if we draw the structure of 3-methylpentane, so if we have 1, 2, 3, 4, 5, 3-methylpentane, and if we're looking down the carbon-2,3 bond like this, which one of these is going to be the most stable conformation? Well, the first thing I would note is that 3-methylpentane has 6 carbons in it. And you can see that in D, we have 7 carbons, right? We have 1, 2, 3, 4, 5, 6, and 7. So D is definitely not an answer. Whereas A, A, B, and C, these are all different Newman projections of this molecule, 3-methylpentane. So if we take a look at these, you can see that B is going to be a high energy because we have 2 gauche interactions here. Now in C, we have a gauche interaction, and in A, we have a gauche interaction. But remember, we're looking for most stable. Now, which one of these two gauche interactions is it going to be this one that I'm highlighting in yellow or this one that I'm highlighting in green that's going to be higher energy? Well, it's going to be C because we have a gauche interaction between a methyl and an ethyl group, whereas here we have a gauche interaction between two methyl groups. And so this one is going to be the most stable conformation. And so the answer is going to be A. All right, number 8 is kind of a quick question. Rank these conformations from least to most stable. We can see that 2 and 3 have a staggered conformation, whereas 1 has an eclipsed conformation. So 1 is definitely going to be the least stable by a long shot. And then in 2, you see the two methyl groups are gauche to each other. Whereas in 3, they are anti to each other. And so 3 is going to be the most stable. 1 would be the least stable. And so the answer is going to be A, 1, 2, then 3 being the most stable, going from least to most. All right, number 9. What's the name of this compound? Well, you see we have a Fisher projection here. We've got um, we've got an aldehyde, and you can see that each one of these names ends in al. We have a total of how many carbons? We got 1, 2, 3. So this is some kind of propanal. They all end in propanal, so we can't use that. If we number the carbons, they would go 1, 2, 3. So this is a 2,3 dihydroxy propanal. So that means we could get rid of the first one because it's not 1, 2 dihydroxypropanal. It would be 2, 3 dihydroxypropanal. All right, so now we need to decide between B, C, and D. Well, you notice that in B and C, they've only assigned one stereocenter, whereas in D, they've assigned two stereocenters. But you can see that carbon 3 is not a stereocenter, right? Carbon 3 is not a stereocenter. I'll just cross that out because it has two hydrogens on it. So now we go between B and C. Which one of these is correct? Well, let me erase all this. And we just need to figure out the chirality at this chiral center. And so this group is going to be the highest priority. The hydrogen is going to be the lowest priority. Second highest is going to be the group with the carbonyl, and 3 will be this group over here. So we're going to go from 1 to 2 to 3. That's going counterclockwise, which is S. But remember, our hydrogen is horizontal, so that means it's on a wedge. So we have to flip that to R. And so this is an R stereocenter. And so our answer is going to be B, R 2,3 dihydroxypropanol. All right, moving right along. What are the configurations of the two stereocenters in this Fisher projection? Now, depending on whether you've completed organic chemistry 2 or not, you might solve this in a different way from somebody who's only completed organic chemistry 1. So I'm just going to solve it applying the Kahn-Ingold pre-log rules. So we'll start with chiral center, the chiral center at carbon number 2. So we have 1, 2, 4, and 3. So we're going 1, 2, 3. So we're going counterclockwise, which would be S, but we flip that to R because the hydrogen is going to be on a wedge. So we know that chiral center 2 is an R, so we can cross these ones off. We delete all that. Then if we go to the chiral center at carbon number 3, we have 1, then we have 2, then we have 3. So we're going from 1 to 2 to 3, which would be S because we're going counterclockwise, but remember our hydrogen is on a wedge, and so we flip the S to R, and so this is 2R, 3R. Number 11, rank these compounds from lowest to highest energy. All right, so we've got some substituted cyclohexanes here. You can see we've got we get an isopropyl group here, isopropyl group here, isopropyl group here. Here we have a methyl group, here we have a methyl group, and here we have an ethyl group. All right, so get some different groups here, but they all have an isopropyl group in common. Now, the lowest energy compound is going to be a compound that's going to be able to have these two substituents, whatever they are, in an equatorial position. So if we just start with number 1, if we imagine that this isopropyl group is up and equatorial, okay, and equatorial. That would mean that this position, this hydrogen that's up, would be up and axial. This one would be up and equatorial. And so this would be up and axial. So that means that even if you flip the conformation of the ring, either the isopropyl group or the methyl group has to be in an axial position. One of them has to be axial. And so now if we apply that same rationale to number 2, if the isopropyl group is up and equatorial, that would mean that this hydrogen is up and axial, and that would mean that this methyl group is up and equatorial. And so both substituents can be in an equatorial position. And so compound number 2 is going to be more stable than compound number 1. And so it's going to have a lower energy. So compound number 2 has to be lower than compound number 1. Now, if we look at compound number 3, we can make a comparison between 1 and 3 because they're both 1,4 disubstituted compounds. So which one is going to be higher energy than the other? Well, either way, you have to have one of the groups being axial. And in that way, we'd be comparing the ethyl group to the methyl group. Well, an ethyl group is higher energy than a methyl group because of 1,3 diaxial interactions. And so that means that compound 3 is going to be the highest energy of all the compounds. And so the order is going to be 2 would be the most stable, 1 would be the second most stable because of the methyl group, and then 3 would be the least stable of these 3. Okay, number 12, which structure is identical to this molecule? There's a couple of different ways you could solve this problem, and probably all of these problems. I'm just solving them the way I did quickly. The first thing you might want to do something like this. You might want to say, okay, methyl group, hydroxyl group. We can see the order is 1, 3, 4. The two methyls are trans. So we have 1, 3, 4. The two methyls are trans. 1, 3, 4. The two methyls are trans. And then 1, 3, 4. The two methyls are trans. 1, 3, 4. The two methyls are cis. So that can't be an answer. Then if we look at the methyl in the hydroxyl group at carbons 3 and 4, respectively, those are cis to each other. And so we can scratch off A because they're trans to each other here. So we can get rid of that. So, then it's, is it B or is it C? Well, you can see that if you were to take your eyeball and look at this compound, if you imagine looking at it from this direction, right? You'd see the methyl group is going down away from you at carbon 1. It's coming up towards you at carbon 3. And the hydroxyl group is coming up towards you at carbon number 4. And so the answer would be C. And of course, compound B would just be the enantiomer of C. All right, what best describes the most stable conformation of trans 1 isopropyl 3 methyl cyclohexane? This goes back to question 11 because we have a 1 isopropyl 3 methyl cyclohexane, but they're cis in compound 2 here. So what we're talking about is we're talking about a compound that looks like this, where we have our isopropyl group. We'll say it's like this. And then we have our methyl group, right? And you can see they're trans to each other. One is going up, one is going down. So what would be the most stable conformation? Well, the most stable conformation is going to be one where the isopropyl group is equatorial. And so if the isopropyl group was up and equatorial, that would mean that this hydrogen is up and axial, and that would mean that this hydrogen is up and equatorial. And so that means that this methyl group is going to be down and axial. All right, and so the answer is going to be A, the isopropyl group is equatorial and the methyl group is axial. You certainly wouldn't want it the reverse, where the isopropyl group is axial and the methyl group is equatorial, right? Because the isopropyl group is going to be higher energy because it has more or higher energy 1,3 diaxial interactions, and there's no way that they can both be equatorial or both be axial. All right, number 14, which compound has the IUPAC name trans 1-chloro-3-ethyl cyclohexane? Well, we can scratch C off the block immediately because it's a 1,3 disubstituted compound, but it's 1-chloro-3-methyl, so we can get rid of that one. We could also get rid of B because we have 1, 2, 3, 4. This is a 1,4 disubstituted compound. Now, if we look at D, you can see that the chlorine here is up and equatorial, and the ethyl group here is up and equatorial. So if they're both equatorial, that means they're both going up in this case. So this would actually be a cis compound. This would be cis 1-chloro-3-ethyl cyclohexane. But in one, you can see that the chlorine is up and equatorial, and the ethyl group is down and axial. So one is up and one is down. And so this is a trans compound. Trans compound. And so the answer is A. All right. Number 15, when you started studying cycloalkanes like cyclopropane, cyclobutane, cyclopentane, cyclohexane, etc., you would have talked about why we spend so much time focusing on cyclohexane in organic chemistry. And it's because it's the most stable of all of the cycloalkanes. And it's because all the carbons in cyclohexane are perfectly um, tetrahedral. If you draw a quick chair like that, all the carbons are tetrahedral with bond angles of 109.5 degrees. Okay. Whereas if you have a compound like what are we talking about here? Cyclopropane. Okay. Um, you can see the bond angles are going to be much smaller. And so there's going to be a lot of ring strain there. So the way they quantify the stability when they compare cycloalkanes is by burning them, so causing them to undergo combustion, and then they divide the amount of heat that's liberated per the number of methylene groups, CH2 groups in the molecule. And so cyclohexane has a different hydrogen to carbon ratio than cyclopropane. No, that's not the reason. Cyclohexane has greater ring strain. No, it has has less ring strain, so that's not true. But cyclopropane is strained relative to cyclohexane. That's definitely true. In fact, I have a model kit in my office where if you can't even make a model of cyclopropane with it. You might think it's kind of silly, but there's good reasons why you can't do that. It's with something called a Feezer model. So I think the spelling is the Feezer. Feezer models. Anyhow, they enable you to flip a cyclohexane ring, so they're pretty cool. You might see them in some of my other YouTube videos. All right, we kind of answered question 16 already. I told you that the bond angles in cyclohexane were 109.5 degrees, which is closest to 110. Which molecules, I think this is a typo in the manual. It should, since there's only one answer, it should be which molecule would have the highest heat of combustion or release most energy when burned to produce carbon dioxide and water. So if we're looking for the highest heat of combustion, it's going to be the highest energy compound or the most strained. So we're looking for the most strained compound because you notice that these are all isomers. They all are C7H14. And so the cyclobutane is certainly going to be the most strained out of all of those. All right, question 18. Which compound is, all right, question 18, which is or are optically inactive? So we're looking for something here with no stereocenters or a meso compound. And if we start with compound number 1, you can see that if you rotate this bond, if you rotate that by 180 degrees, you're going to see that you'll have a meso compound. So you would have something, drawing it as a sawhorse diagram. It's actually kind of annoying, but anyhow, I'll do it. So we'll leave the methyl group here. Our hydroxyl would be like this. Hydroxyl is here. So if we rotate that bond 180 degrees, what you'd end up with is with the hydroxyl here, okay? And then when you do that, the methyl is going to be in the back. So the methyl is going to be over here, CH3, and then you have the hydrogen over here. So this is not a meso compound. So not meso. And so this compound is optically active. If we look at number two is a meso compound. Okay, if you rotate the carbon-carbon bond between this carbon and the carbon behind it, if you rotate that 180 degrees, you would see that this methyl group is going to come up here, and then this hydroxyl group is going to come over here. So they're going to overlap, all right? So that is definitely a meso compound. So that compound is optically inactive and one isn't. So yeah, that only crosses off A so far. So then if we look at compound number 3, you can see it doesn't have a plane of symmetry in it, and you have two chiral carbons, right? You have one here, and you also have one here. Those are the only two chiral carbons, and this certainly is not a plane of symmetry here, right? Over here we have a hydroxyl and a methyl. Here we have a hydroxyl and an ethyl. And so that is definitely an optically active compound. And so the answer is going to be only compound 2, the meso compound. It's the only one that's going to be optically inactive. Question 19 is asking, excuse me, the same thing. Which molecule is not optically inactive, or which molecule is optically inactive? And here you can see the A is a meso compound. This is a meso compound. And so it's optically inactive. If we go to 20, which compound is optically active? Well, if you look at A, you can certainly tell this is a meso compound. And so it's optically inactive. It is meso. If you look at B, there's no chiral centers in it. So that's not optically active. And C kind of fools you maybe. It might trick you into thinking that it has chiral centers, but it doesn't, right? So if you look at this carbon here and you say, well, that's a chiral center. No, because if you follow the pathway on this side or this side, you end up with the same thing. So there's no chiral centers in this molecule, okay? It also has an internal plane of symmetry, which is a meso, kind of like a meso-like situation. Now, in this compound, we have a nice juicy chiral center, and so this is definitely an optically active compound. All right, question 21. What's the IUPAC name for this compound? So whenever I'm asked a question in these ACS study guides or an ACS exam, anything that has E and Z on it, I start with that immediately. Okay, so I look at the double bond and I say, well, the chlorine has the higher priority than this carbon. So this is the highest priority. And obviously this group has a higher priority than this hydrogen down here. And so this is a Z compound, right? This is a Z compound, so I'll just write Z up here. And so that way we can scratch off these ones right away. All right. Now we need to try to figure out the rest of the naming. So we're going to start here. We want to give that double bond the lowest possible numbering we can. So 1, 2, 3, 4, 5, 6. We have a chloro and a fluoro. The chloro should come first. And so we have a 3-chloro, 1-fluoro, 2-hexene, and it's a Z compound. And so the answer is going to be A for this one. All right, number 22, which compound is E? 1,2-dichloro, 2-pentene. Again, I mean, you could probably, just do the counting. That would work, but I like to do the E and Z. And so if we look at A, we see this group has a higher priority, so this is an E compound. If we go to B, we have this group, and so this is a Z compound, so we can scratch that one off. We go to C, we can see right away that this is a trans compound, so it's an E compound. And then if you look at D, you can see these two hydrogens are cis to each other, and so this is a Z compound. So we got rid of B and D immediately. All right, so 1,2-dichloro, 2-pentene. So we're gonna start numbering here. 1, 2, 3, 4, 5. So this is a 2-pentene. You got chlorines at carbons 1 and 2, and so this had better be the answer. If you look at compound B, so compound B, we'd start here 1, 2, 3, 4, 5, and so that would be 4, 5-dichloro, 2-pentene. So can't be the right answer. So the answer is A. Number 23, still get that E and Z thing going on here. So we can see that the highest priority group on this carbon is going to be the ethyl group. The highest priority group on this carbon is going to be all this spinach over here. So this is a Z compound. That doesn't do a lot for us, does it? It only allows us to eliminate one compound. All right, but we have two functional groups in the compound, don't we? We have an alkene and an alcohol. Well, remember the alcohol takes precedence, and you can clearly see that because they all end in the suffix "all." But since the alcohol takes precedence, we want to give it the lowest possible number when we're numbering the longest carbon chain. So we have 1, 2, 3, 4, 5, 6, 7, like this. So it would be 2 all. So we can cross off this one. And so you can see we have a methyl group at carbon 5, and so the correct answer is going to have to be D, which would be Z5-methyl, 4-heptene. So remember, the 4-heptene, you see the E here, that denotes that there's an alkene here, and it starts at carbon number 4, so the correct answer is D. All right, number 24. What's the IUPAC name of this compound? I don't know. Let's figure it out. All right, so if we look at this first double bond here, we got two double bonds in this compound, so it's some kind of diene. But you know that when you have a double bond and you have two substituents that are identical on one of the carbons, there's no E or Z. So this double bond is not E or Z. Same thing, it's not cis or trans. So we can scratch off these ones right away. So now we only have to focus on the other double bond, this one here, and answer, is this an E or a Z compound? Well, we can clearly see it's an E compound because it's trans, okay? You have the two hydrogens like this, right? So the answer is going to be A. It's going to be E25 dimethyl hexa 1,3 diene. All right, number 25, which pair of compounds are enantiomers? I find this question kind of weird, and maybe somebody can comment in the video. First of all, you can see that these compounds here are meso compounds, so they're achiral compounds. So these are meso. And in this one, in B, you can see this chiral center is the same, but these two are different. And so these two compounds would be diastereomers of each other. Now, in the solutions, it says that D is the answer, and you can see that these are clearly mirror images of each other. Okay, if we look like this, you can see they're mirror images, right? They flipped this chiral center, and then they flipped the other one. Anyhow, but it also looks to me like C is a pair of enantiomers, if I'm not mistaken. But anyhow, they put D as the answer. So I guess we'll just leave it at that. Anyhow, maybe there's something I'm missing there. Anyhow, which structure represents a meso compound? I don't know if the people at ACS were getting tired, because it feels like we were asked this exact same question earlier on when it asked us which one of these is an achiral compound. And so we have two chiral centers, but we have a plane of symmetry in the molecule. And so this is a meso compound. How are these molecules related? Are they identical enantiomers, diastereomers, constitutional isomers? Well, you can see that if you were to just draw a line here in your mind, and if you were to rotate this 180 degrees, you'd see these two compounds are identical to each other. Now, there's other things you could do. Um, you could say, sometimes students might look at this and say, yeah, but they flipped the two stereocenters. Yes, but that would only count if they hadn't changed the orientation of the carbon of the longest chain, right? If you were to take, like, let's say you were to redraw this first compound like this. Oops, I'm doing what I wasn't supposed to do. Let's say you were to redraw this chain like this, and then you change this to a wedge, and you change this to a dash. These two compounds would be enantiomers of each other, okay? But the two compounds that are in the box, it's the same compound, just drawn twice. All right, number 28, how are these molecules related? I think they're, cousins twice removed or something. No, anyhow, let's take a look here. So we want to look down the axis between this carbon and this carbon, because that would give us a Newman projection. So if we draw an eyeball, that's what I'm doing here when I do this. This is an eyeball. We look down this carbon axis, what would we see? Well, let's draw it. Okay. We would have we'd have an ethyl group going straight up like this. We'd have a bromine going to the left hand side, right? This bromine would be going to the left, and so this proton would be going to the right. In the back, we have the methyl group going straight down. I'll put CH3 to be consistent with them. Then we'd have the hydroxyl on the same side as the bromine. like this, and then we have the proton over here like this. Now, if you compare this and this, right, what do you see? You see that they are mirror images of each other. And so these two compounds are enantiomers of each other. There's other ways you could solve this problem. You could try to redraw the Newman projection that's shown here. You try to redraw this as a bond line structure and then assign R and S, and you'd see that that the stereocenters change for each one of the chiral carbons. Either way works. All right, number 29, how are these molecules related? Well, you can see we've got a few chiral centers here. This one and this one are identical. This one and this one are identical. But then here, they flip them, all right? So these are stereoisomers, but they're not enantiomers. Therefore, they are diastereomers of each other. All right, and question 30 is in the same vein as question 29, believe it or not. It says, what's the configuration or stereochemical classification of 1s, 2s, 1,2-cyclohexane diol, and 1r, 2s, 1,2-cyclohexane diol? No need to draw anything here whatsoever. If you have 1s, 2s, okay? Now, if you were to flip both of those stereocenters to 1r, 2r, then these compounds would be enantiomers, right? But you're only flipping one of the stereocenters, right? You're just flipping the first one, so 1r and then 2s, like this. So they're the same at one stereocenter, they're opposite at another stereocenter, and so they're not enantiomers, but they're stereoisomers. Therefore, they are what? Diastereomers. And so the answer is going to be B. I hope you found this video helpful. Now, again, these are just the ways that I solved them relatively quickly. I just put this up here in case it helps anybody who's probably preparing for, their organic chemistry 1, ACS final, or maybe organic chemistry 2. And maybe if you're preparing for an MCAT or a DAT exam or something like that. I hope you find this helpful.